Tonight, we're going to explore something that quietly and permanently altered the way every human being on this planet understands the cosmos. We're going to journey through the full story of the Hubble Space Telescope, not just as a piece of engineering, but as an idea that took 50 years to be born, nearly died in disgrace in its first weeks of life, and then rose to become the most scientifically productive instrument in the history of our species. By the end of this journey, you're going to understand exactly what Hubble saw, how it changed what we thought we knew, and why the images it sent back to Earth will be considered among the most important photographs ever taken for as long as human civilization endures. Before we begin, if you enjoy these deep, slow explorations of our universe, a like and subscribe would mean a great deal and help the channel reach more curious minds. Now, let's settle in. Let's go slowly. And let's begin right at the very beginning with a problem that has haunted astronomers since the first person ever tilted their head toward the stars. Section 1. The Dream Before the Machine. There is something deeply and persistently frustrating about being human and trying to understand the universe from the bottom of an ocean of air. For thousands of years, our only window to the cosmos was the naked eye, and the night sky it revealed was magnificent in its own right. Stars wheeled overhead in their ancient patterns. The band of the Milky Way arced across dark, rural nights. Ancient civilizations built entire religions and calendars around what they could see, and they weren't wrong to find the sky profound. Then, in the early 17th century, Galileo Galilei turned a crude magnifying instrument toward the heavens, and overnight the sky multiplied in complexity. Mountains on the moon, satellites orbiting Jupiter, spots on the face of the sun. Within decades, it was obvious that telescopes would be the primary tool through which humanity would read the universe. But even as telescope technology advanced over the following centuries, there remained an inescapable limitation. Earth is wrapped in a thick, turbulent blanket of air that is never perfectly still. It churns in countless invisible eddies and temperature gradients, and every beam of light passing through it is bent, scattered, and distorted. When you look at a star and see it twinkle, you are watching that distortion in action. The star is perfectly steady. It is your atmosphere that shakes. And for astronomical observation, that shaking is a catastrophe. No matter how large the mirror or how exquisite the glass, every ground-based telescope is ultimately defeated by the air it sits beneath. Astronomers lived with this limitation for 300 years, but the man who truly championed the idea of escaping it, who spent 5 decades lobbying, arguing, and convincing everyone around him that it could and must be done, was an American astrophysicist named Lyman Spitzer. In 1946, Spitzer was 32 years old, recently returned from wartime sonar research, and recruited to participate in a think tank assembled for the Rand Corporation. He used the opportunity to write a paper titled Astronomical Advantages of an Extraterrestrial Observatory. It was classified despite its innocent-sounding name. It appeared as an appendix in a long policy document that most working scientists would never see. And yet Spitzer knew, with absolute clarity, what he had written. He knew it was important. He knew it was right. For the next 51 years of his life, he never let the idea go. Spitzer outlined 2 primary advantages of a space-based telescope. First, Earth's atmosphere absorbs enormous portions of the electromagnetic spectrum. Ultraviolet radiation is almost entirely blocked, as is most infrared. So a telescope above the atmosphere would have access to wavelengths completely invisible to any ground. Observatory. Second, freed from atmospheric turbulence, the instrument's theoretical resolving power would be limited only by optics and mirror size, not by shimmering air. He argued the primary contribution of orbital observatories would be not to supplement our present ideas of the universe we live in, but rather to uncover new phenomena not yet imagined, and perhaps to modify profoundly our basic concepts of space and time. The process of making it real was maddeningly slow. Through the 1950s and 1960s, Spitzer chaired committees, traveled to Washington, lobbied congressmen. The European Space Agency was brought in as a partner in 1975, contributing roughly 15% of costs, and their participation helped secure congressional approval in 1977. The telescope was formally named the Hubble Space Telescope in 1983, honoring Edwin Hubble, whose 1929 discovery of the expanding universe was one of the core scientific problems the new instrument would address. Construction began, and almost immediately, nothing went smoothly. Section 2. Building the Eye of God. The heart of the entire telescope was the primary mirror, 2.4 meters in diameter, about 7.9 feet, and needing to be polished to a surface accuracy of roughly 10 nanometers, 1/65th the wavelength of red light. NASA assigned the optical assembly to Perkin-Elmer Corporation in Danbury, Connecticut, while Lockheed Missiles and Space Company built the spacecraft structure. Multiple NASA internal reports questioned Perkin-Elmer's management, and the polishing schedule fell behind budget and behind schedule. To save money, NASA canceled a backup mirror that had been commissioned from Eastman Kodak, a decision that eliminated the independent cross-check that might have caught what was about to happen. The Kodak-Tech joint bid for the original mirror contract had been higher than Perkin-Elmer's, but it included 2 independent verification tests. Perkin-Elmer's cheaper bid offered no such redundancy. The cost saving would later look like the most expensive economy in the history of science. The mirror was completed in 1981, coated with a reflective layer of aluminum and a protective overcoating of magnesium fluoride. Additional delays accumulated as the rest of the telescope came together. The original 1983 launch target slipped to 1985, then to October 1986, before being overtaken entirely by the most catastrophic event in NASA's history. On January 28, 1986, the Space Shuttle Challenger disintegrated 73 seconds after launch, killing all 7 crew members and grounding the shuttle fleet for more than 2 years. For Hubble, the delay provided unintentional improvements. Technicians upgraded the solar panels, improved computer systems, enhanced redundancy capabilities, and redesigned the aft shroud to make future instrument replacements easier. Finally, on April 24, 1990, Space Shuttle Discovery lifted off from Kennedy Space Center with the Hubble Space Telescope, secured in its cargo bay. The following day, mission specialist Stephen Hawley deployed it into orbit 340 miles above Earth, traveling at roughly 28,000 kilometers per hour. The instrument that Lyman Spitzer had dreamed of in 1946 was open for business. What happened next was not what anyone had hoped. Section 3. The flaw that nearly ended everything. The first images from Hubble arrived in the weeks following deployment, and what astronomers saw immediately made their stomachs drop. Stars that should have been sharp points of light were surrounded by large, soft halos. The fine detail Hubble was designed to reveal, the detail that justified its $1.6 billion price tag, was simply not there. NASA made a formal announcement on June 27, 1990. The primary mirror was flawed. Its outer edge was too flat, ground to the wrong shape by approximately 2.2 microns, about 1/50th the width of a human hair. The error was called spherical aberration, and while tiny in physical terms, it was 10 times larger than the tolerance the optical design required. Light reflecting off the edge of the mirror focused at a different point than light from the center. No single clean focal point existed. Every object Hubble tried to observe was surrounded by a diffuse halo of misdirected light. The political and media fallout was ferocious. Senator Barbara Mikulski of Maryland called Hubble a techno-turkey. Late-night television comedians mocked the agency. For a public still raw from the Challenger disaster 4 years earlier, a billion-dollar telescope that couldn't focus felt like yet another sign of institutional failure. A board of investigation chaired by Lou Allen, director of the Jet Propulsion Laboratory, determined the cause. The null corrector, the testing device used to verify the mirror's shape during fabrication, had been incorrectly assembled. One small lens within the device was installed 1.3 millimeters out of position. This tiny misplacement caused the null corrector to report that the mirror was perfectly formed, when in fact it was systematically wrong. Perkin-Elmer's engineers had polished the mirror with extraordinary skill and care. The instrument telling them they were doing it right was itself lying. Making this worse, during the polishing process, conventional null correctors had actually indicated spherical aberration. Those results were noted in the documentation. They were dismissed as artifacts of the conventional instrument's own limitations, since the custom-built reflective device kept returning clean results. Nobody understood that the custom instrument was the one that was wrong. The correct measurements were the ones being ignored, and the Kodak backup mirror, which would have provided an immediate comparison, had been canceled. The flaw reached orbit because the system designed to catch it had been eliminated to save money. Section 4. The greatest repair job in history. There was one unusual feature of Hubble's design that in the terrible weeks after the mirror flaw announcement began to look less like an afterthought and more like extraordinary foresight. The telescope had been designed to be serviced by astronauts in orbit. Its instruments were packaged in standardized modules that could be extracted and replaced like circuit boards. This serviceability had been built in simply because technology would advance and better instruments would become available. Nobody had anticipated a catastrophe like the mirror flaw, but the fact that servicing was possible at all was the reason Hubble could be saved. The mirror itself could not be replaced in orbit, but corrective optics could be installed to compensate for its error before the light reached the scientific instruments. For the main camera, a replacement with built-in compensating optics was already being developed. For the other instruments, a device called COSTAR, the Corrective Optics Space Telescope Axial replacement, was engineered. 5 pairs of small corrective mirrors on motor-controlled deployable arms with 12 motors and more than 5,000 individual parts. When deployed, these mirrors would intercept the flawed light from Hubble's primary mirror and redirect it, corrected for the spherical aberration, into the entrances of the other scientific instruments the crew selected for servicing mission. One was 7 astronauts aboard Space Shuttle Endeavour, launched December 2nd, 1993. Their spacewalkers, Story Musgrave, Jeffrey Hoffman, Catherine Thornton, and Thomas Akers, had rehearsed every procedure exhaustively in NASA's enormous neutral buoyancy facility. Musgrave, who had been involved with Hubble since the telescope's early development, knew the structure intimately. Over 5 days of extravehicular activity, totaling approximately 35 hours and 28 minutes, the crew installed co-star, replaced the main camera, swapped the solar panels and gyroscopes, and upgraded the flight computer. When Endeavour undocked and the telescope was released back into orbit, the world held its breath. 2 weeks later, the first corrected images arrived. The reaction at the Space Telescope Science Institute was stunned, joyful disbelief. Stars were perfect points of light. Chief scientist Edward Weiler said the results were fixed beyond our wildest expectations. A before and after comparison of Galaxy M100 told the story in a single devastating image. The before was a blur. The after was a masterpiece. The telescope that had been called a techno-turkey was, overnight, the most admired scientific instrument on Earth. And it was just beginning. Section 5. The Deep Fields. Windows to the Beginning of Time. By 1994, Hubble was operating at full capacity. Every observation cycle was oversubscribed by a factor of 6 or 7 to 1. Robert Williams, who had become director of the Space Telescope Science Institute in Baltimore, was thinking about something more ambitious, pointing the telescope at nothing. Up to 10% of Hubble's observation time is allocated at the director's discretion. Williams decided he would devote a significant fraction of his to a single audacious experiment. He wanted to take the deepest photograph ever made of the universe, not of any known galaxy or nebula, but simply of the sky itself, in a direction that looked as empty as possible, to see what was there that nobody had ever seen before. The team needed a patch of sky away from the bright plane of the Milky Way, away from the zodiacal light, in a continuous viewing zone where Earth wouldn't block the line of sight during orbit, and clear of nearby bright objects. They settled on a region in Ursa Major near the handle of the Big Dipper, a patch of apparent sky so featureless that it contained almost nothing recognizable in existing catalogs. Between December 18th and December 28th, 1995, Hubble stared at that patch of apparent emptiness for 10 consecutive days, accumulating 342 separate exposures, totaling more than 100 hours. For comparison, most Hubble observations at the time range from a few minutes to a few hours. The patch being observed was roughly equivalent to the area you see holding a pinhead at arm's length against the sky. When the data was processed, what astronomers saw changed how humanity understood its place in the universe. The image was not empty. Every corner of that tiny pinhead-sized patch of apparent nothing was filled with galaxies, not dozens, not hundreds. Approximately 3,000 separate galaxies were identified in that single image. Familiar spirals and ellipticals, alongside bizarre objects with no names in any existing catalog, tiny blue smears, irregular fragments, distorted wisps of light, These were galaxies as they existed when the universe was young, billions of years before the orderly structures we see today had fully assembled themselves. The light from the most distant objects in that image had been traveling for more than 10 billion years before it reached Hubble's mirror. When Williams presented the results at a meeting of the American Astronomical Society in January 1996, the assembled astronomers were stunned. The Hubble Deep Field demonstrated the sheer density of galaxies in every direction and provided the first clear window into the deep past of galaxy formation. The distant galaxies were small, irregular, often in the process of merging with one another, caught in the act of building the larger structures we see closer to us in time. The deep field was not a photograph of the distant universe. It was a photograph of the universe's childhood. Williams made the entire dataset immediately public, allowing the whole astronomical community to work with it from day one. Astronomers identified a large population of very high redshift galaxies, objects so distant that their light, originally emitted in ultraviolet, had been stretched by cosmic expansion all the way to infrared before reaching Earth. A 1998 infrared follow-up identified galaxies believed to be over 12 billion light-years away. Data confirmed that the rate of star formation in the universe peaked around 8 to 10 billion years ago and has been declining ever since. A second deep field was observed in the southern hemisphere in 1998 to confirm that what had been seen was representative of the whole sky. It was. In 2004, using the newly installed advanced camera for surveys, the team created the Hubble Ultra Deep Field, a million-second-long exposure accumulated over 400 orbits. It contained approximately 10,000 galaxies, with some of the most ancient objects ever directly observed. Galaxies that existed only 400 to 800 million years after the Big Bang. In 2012, the extreme deep field pushed deeper still, combining a decade of observations into a composite containing 5,500 galaxies, and a team working with this data identified primitive galaxies from when the universe was just 3% of its current age, approximately 470 million years after the Big Bang. Astronomers used these images to estimate the total number of galaxies in the observable universe. A comprehensive analysis based on the deep fields and improved models suggests the number is closer to 2 trillion. Every one of them a vast system of hundreds of billions of stars, each star potentially circled by planets, each planet a world. The deep fields did not answer whether we are alone, but they made the scale of the question undeniably, permanently clear. Section 6. Measuring the Universe. The Hubble Constant. From the very beginning, one of the most important scientific justifications for building the Hubble Space Telescope was to answer a question causing arguments among astronomers for most of the 20th century. How fast is the universe expanding? And therefore, how old is it? The expansion of the universe had been discovered by Edwin Hubble in 1929, using redshift measurements of distant galaxies. The proportionality constant in the relationship between a galaxy's distance and its recession velocity is now called the Hubble constant, usually written as h0. Knowing its value matters enormously. A higher value means a faster expansion and a younger universe. A lower value means a slower expansion and an older one. In the decades before Hubble launched, estimates of the universe's age range from 9.5 0.7 billion years to 19.5 billion. A factor of 2 uncertainty on one of the most basic properties of the cosmos. The key to measuring the Hubble constant is measuring distances to galaxies accurately. The most important tool for this is a special class of variable stars called Cepheid variables, named after the prototype Delta Cephei. Cepheids pulsate in a regular cycle, brightening and dimming over periods, ranging from a few days to a few months. The crucial property, discovered in 1908 by Harvard astronomer Henrietta Swan Leavitt, is that a Cepheid's pulsation period is directly related to its intrinsic luminosity. Measure how long a Cepheid takes to complete one cycle, and you know how bright it truly is. Compare that to how bright it appears from Earth, and you can calculate the distance. One of Hubble's explicit design goals was to push Cepheid measurements to galaxies 10 times farther away than ground-based telescopes could reach. The Hubble Key project, led by astronomer Wendy Friedman of the Carnegie Institution of Washington, used the telescope's time, over many years, to observe Cepheids in 18 different galaxies out to 65 million light-years, identifying almost 800 individual variable stars. After careful corrections for interstellar dust, the team published their final results in 2001. The Hubble constant was approximately 70 kilometers per second per megaparsec, giving a universe approximately 12 to 14 billion years old. The embarrassing factor of 2 uncertainty had been reduced to roughly 10%. Cosmology had become a precision science, but the story did not end there. As measurements improved, a persistent and troubling discrepancy emerged. Hubble's observations of Cepheids and Type 1a supernovae consistently returned a Hubble constant of around 73 to 74 kilometers per second per megaparsec. An entirely independent measurement derived from the cosmic microwave background radiation, the first light released in the universe, mapped by the European Space Agency's Planck satellite, gave a value of about 67 to 68. These two numbers should agree. They are both measuring the same fundamental property of the same universe, but they don't. They differ by about 9%, which is enormous in a scientific context where both measurements claim uncertainties of only a few percent. This discrepancy is called the Hubble tension, and it is one of the most discussed puzzles in modern cosmology. In 2023, the James Webb Space Telescope confirmed Hubble's Cepheid measurements with high confidence. The tension did not go away. Adam Rees, who shared the 2011 Nobel Prize in Physics partly for his work on the Hubble constant, said the results showed they could rule out a measurement error as the cause of the Hubble tension with very high confidence. What remains, he added, is the real and exciting possibility that we have misunderstood the universe. One of Hubble's original primary missions was accomplished with extraordinary success, and in succeeding, it found a deeper mystery beneath. Section 7, Dark Energy and the Accelerating Universe. In the late 1990s, 2 independent teams of astronomers were racing to answer what seemed like a straightforward question. How much has gravity slowed down the expansion of the universe since the Big Bang? They knew it was expanding. They assumed reasonably that the gravitational attraction between all the matter in the universe must be acting like a brake, gradually decelerating the cosmos as it aged. They wanted to measure how much. To measure the deceleration, both teams turn to the most luminous explosions in the universe. Type 1, a supernovae. These are explosions of white dwarf stars, the compact remnants left when medium-mass stars die, that have been pushed over a critical mass threshold by material drawn from a companion star. Because the trigger mass is always essentially the same, the resulting explosions are all approximately the same intrinsic brightness, making them excellent standard candles, visible across billions of light years. The Hubble Space Telescope was a critical tool for both teams, providing the sharp images needed to distinguish a supernova's light from its surrounding galaxy and measure it precisely. The High-Z Supernova Search Team, led by Brian Schmidt and including a young researcher named Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, both found the same thing. The distant supernovae were fainter than they should have been if the universe were decelerating under gravity. Fainter meant farther away than expected. And farther away than expected, at the measured redshifts, meant only one thing. The expansion of the universe was not decelerating. It was accelerating. When Rees ran his analysis, he looked at the numbers and then looked again, because the answer seemed impossible. He told his supervisor, Robert Kirshner, what the data appeared to be saying, and Kirshner reportedly called it scientific poison ivy. Too astonishing to take seriously without the most rigorous scrutiny. Perlmutter's team, working independently in Berkeley, arrived at the same conclusion through the same process of stunned, reluctant analysis. In early 1998, both teams published essentially simultaneously. Science magazine named the discovery its breakthrough of the year. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics. The accelerating expansion meant something was pushing outward against gravity, overcoming the gravitational attraction between galaxies. This something was named dark energy by cosmologist Michael Turner of the University of Chicago. Dark energy accounts for approximately 68 to 70% of all the energy content of the observable universe. All the matter, stars, planets, gas, dust, and the invisible dark matter accounts for only about 32%. The normal matter making up everything you can see, touch, and measure accounts for only about 5% of the universe's total energy budget. We live in a cosmos almost entirely made of things we do not understand. What dark energy actually is remains one of the greatest open questions in all of science. The most mathematically natural explanation is that it is a property of space itself, an intrinsic energy density built into the fabric of the vacuum, often associated with what Einstein called the cosmological constant, a term he introduced in 1917 and later abandoned when Hubble discovered the expansion. If dark energy is the cosmological constant, the universe will expand forever, growing colder and emptier as galaxies drift apart and stars eventually extinguish. If it is something dynamic and growing stronger with time, the expansion could accelerate without limit until, in the remote future, it tears apart galaxies, then solar systems, then planets, then atoms, a scenario cosmologists call the Big Rip. Hubble's role extended well beyond the initial discovery. Adam Rees subsequently used the telescope to find Type 1, a supernovae, at redshifts greater than 1. So distant their light was emitted when the universe was less than half its current age. These observations confirmed that the early universe was indeed decelerating, dominated by matter's gravity just as old models assumed. Only relatively recently, roughly 5 to 6 billion years ago, did dark energy become strong enough to begin driving the acceleration we observe today. The universe began its life decelerating, switched at some point to accelerating, and we appear to live in that accelerating era. Section 8: Black Holes and the Hearts of Galaxies. Before Hubble launched, astronomers had good theoretical reasons to believe that supermassive black holes containing millions or billions of solar masses existed at the centers of most large galaxies. The energy output of quasars seemed to demand something capable of converting matter to energy with enormous efficiency, and accretion onto a supermassive black hole was the most physically plausible candidate. But belief and proof are different things. In 1994, just months after the servicing mission restored Hubble's optics, the telescope's faint object, camera, observed the center of the giant elliptical galaxy Messier 87, located approximately 54 million light-years away in the Virgo cluster. It found a whirlpool of hot, ionized gas orbiting the galaxy's core at roughly 1.2 million miles per hour. Only a supermassive black hole could produce a gravitational field strong enough to accelerate gas to such speeds at such close range. The mass was calculated at about 2.6 billion times the mass of the Sun, a gravitational titan lurking at the heart of that enormous galaxy. This was the first time astronomers had directly measured the mass of a supermassive black hole in another galaxy by observing the motions of material orbiting it, and it was definitive. But Hubble did not stop with M87. In the years that followed, the telescope conducted a systematic survey of nearby galaxy nuclei, observing orbital velocities of stars and gas at the centers of dozens of different galaxies. The results were remarkable. Supermassive black holes appeared to be present at the centers of virtually every large galaxy examined. Not some of them, not most of them, essentially all of them. What emerged was even more striking than simple ubiquity. Astronomers Laura Farah-Rees and David Merritt, using Hubble data, published in 2000 a remarkably tight relationship between the mass of a supermassive black hole and the velocity dispersion of stars in the surrounding galactic bulge, the M-sigma relation. This has been described as one of the most important discoveries to emerge from the entire Hubble program. The black hole at the center of a galaxy and the stellar population of its bulge co-evolved. Their growth is coupled across scales that span from the tiny event horizon to the sprawling volume of the bulge. The most widely favored explanation invokes feedback. As a black hole grows and consumes material, the energy it releases heats the surrounding gas, eventually expelling it from the galaxy entirely, shutting off both the gas supply to the black hole and the star formation in the bulge simultaneously. The black hole regulates its own growth and the growth of the surrounding stellar population, producing the tight correlation that Hubble revealed. Before these observations, supermassive black holes were thought of as exotic curiosities present in galaxies, but not particularly important to how those galaxies worked. After Hubble, the black hole became a core component, linked by a feedback relationship to the galaxy's entire star-forming history. Section 9: Stellar Nurseries, Death, and the Pillars of Creation. No image produced by the Hubble Space Telescope is more famous, more widely reproduced, or more immediately recognizable than the one released in November 1995, showing three enormous columns of interstellar gas and dust rising from a dense cloud in the Eagle Nebula, about 7,000 light-years away in the constellation Serpens. Those columns were named the Pillars of Creation, and the name entered the permanent vocabulary of both astronomy and popular culture simultaneously. The photograph was taken by astronomers Jeff Hester and Paul Scowen from Arizona State University, studying the phenomenon of photoevaporation, the process by which ultraviolet radiation from hot, newly formed stars erodes the surrounding gas. The Eagle Nebula contains a young cluster of massive stars that pour out fierce ultraviolet radiation, ionizing and blowing away the surrounding diffuse gas. But denser clumps of gas resist this erosion more effectively. They act as shields, protecting the material behind them, and gradually protrude above the eroded plane as elongated columns. At the tip of each pillar, shielded from the worst of the radiation, new stars are forming inside the compressed gas. The tallest of the three main pillars stretches approximately 4 light-years from base to tip, essentially as tall as the distance from the Sun to Proxima Centauri. The glowing colors in the famous image are not the true colors you would see with your eyes. They are a visual translation of specific emission lines: hydrogen, oxygen, and sulfur, each assigned a color to convey the chemistry of the gas. In 2014, for the 25th anniversary of Hubble's launch, astronomers rephotographed the pillars with improved technology, revealing faint jets from newly forming protostars shooting from the pillars' flanks, and a comparison showing subtle structural changes over the 19 years between the two images. But the Eagle Nebula is one example within a much larger category of Hubble science. The telescope imaged the Orion Nebula, the nearest major stellar nursery to the Sun at roughly 1,344 light-years, in a massive mosaic that resolved thousands of young stars, including hundreds of protoplanetary disks, flattened clouds of gas and dust from which planets were actively coalescing, in some cases being simultaneously evaporated by radiation from nearby hot stars. These observations confirmed that planet formation is not rare, but a natural consequence of star formation, happening in vast numbers simultaneously across every star-forming region. The deaths of stars were matched in Hubble's archive by equally striking imagery: the Crab Nebula, the remains of a supernova observed by Chinese astronomers in 1054 CE, was imaged in a panoramic mosaic, showing the tangled web of filaments and complex structure around the pulsar at its heart, still expanding at roughly 1,500 kilometers per second. Planetary nebulae, the glowing shells shed by dying sun-like stars, were revealed as objects of extraordinary complexity: nested shells, bipolar jets, spiral patterns, rings within rings. Before Hubble, these appeared as simple blurs in ground-based images. With Hubble's corrected vision, they became laboratories for studying the final stages of stellar life. Every molecule in your body was forged in a stellar furnace and scattered by a stellar explosion, probably many generations of them, before eventually condensing into the solar nebula from which Earth formed. Hubble's observations of stellar birth, death, and the interstellar medium filled in the details of this process across a wide range of environments, building a comprehensive picture of the stellar life cycle fundamental to understanding not just astronomy, but chemistry, geology, and ultimately biology. Section 10. planets, exoplanets, and the legacy that will never fade. Long before the field of exoplanet science even existed, the Hubble Space Telescope was already contributing to our understanding of the solar system. The telescope was not conceived as a planetary science instrument, but its resolving power and ability to monitor over long periods gave it a unique role. The most dramatically timed demonstration came in July 1994, less than a year after the servicing mission restored its optics. Comet Shoemaker-Levy 9, torn apart by Jupiter's gravity in 1992, impacted Jupiter as a chain of more than 20 fragments between July 16th and 22nd, 1994. The combined force of the impacts has been estimated at roughly 300 million nuclear weapons. They created plumes of superheated gas extending 1,200 to 1,900 miles above Jupiter's cloud tops, and left dark, ringed scars the size of Earth. Visible in Hubble's images, the telescope's ultraviolet observations tracked fine debris particles in Jupiter's upper atmosphere, revealing high-altitude wind patterns for the first time. The dramatic, crisp images went around the world, only in newspapers and on television screens, announcing to a global audience that this once mocked telescope was now among the most extraordinary scientific instruments ever built. Hubble discovered 4 of Pluto's 5 known moons: Nix and Hydra in 2005, Kerberos in 2011, and Styx in 2012. These discoveries were critical to planning the New Horizons mission's 2015 flyby, and Hubble subsequently helped locate Arrokoth, the Kuiper Belt object New Horizons flew past on January 1, 2019. In 2015, observations of aurorae around Ganymede, Jupiter's largest moon, revealed through the subtle rocking of those aurorae that the moon harbors a subsurface ocean of salt water approximately 100 kilometers deep, trapped beneath 150 kilometers of ice. An ocean containing more liquid water than all of Earth's oceans combined, discovered by a telescope studying auroral patterns from 340 miles above Earth. In exoplanet science, Hubble's contributions were remarkable, given the field barely existed at the telescope's launch. In 2001, using the Space Telescope imaging spectrograph, it made the first ever detection of an atmosphere around a planet orbiting another star. The planet was HD 209,458b, a hot Jupiter about 150 light-years from Earth. As the planet transited its star, Hubble measured how the starlight changed at different wavelengths and detected a clear absorption signature of sodium in the planet's atmosphere, the first time any chemical element had been detected on a world beyond our solar system. This observation opened the entire field of exoplanet atmospheric characterization. Over the following years, Hubble detected water vapor, carbon dioxide, methane, and potassium in other exoplanet atmospheres. It produced what was described as the most detailed weather map ever made for an exoplanet, tracing cloud patterns as a hot Jupiter orbited its host star. The Hubble Space Telescope has now been in operation for more than 3 decades. It has made over 1.5 million separate observations. The scientific papers based on its data have been cited approximately 800,000 times, making it one of the most productive scientific instruments in human history. It has contributed to discoveries in virtually every area of astronomy, There is no major question in modern astrophysics that Hubble's data has not touched. After the first servicing mission in 1993, four more followed: 1997, 1999, 2002, and a final mission in 2009 that followed a terrifying cancellation in the wake of the Columbia disaster and an equally dramatic reinstatement. Each mission kept Hubble alive and upgraded its capabilities. The Wide Field Camera 3, installed in 2009, remains among the most capable astronomical instruments ever sent to space. The telescope has no more servicing missions planned. When it eventually fails, a gyroscope wearing out, a power system going dark, it will re-enter Earth's atmosphere and burn. There is no rescue planned. The James Webb Space Telescope, launched on December 25, 2021, is its spiritual successor and complement, with a 6.5-meter mirror optimized for infrared, able to observe the universe's first 100 million years. But Webb and Hubble are partners, not replacements. Simultaneous observations with both have already produced science neither could achieve alone. When Hubble is gone, nothing in existence will fully replace its ultraviolet and visible light capabilities from outside the atmosphere. That loss, when it comes, will be real. But what Hubble has already done cannot be undone. The photographs are permanent. The data is archived. The deep fields have changed how human beings understand the scale and contents of the observable universe. The measurement of the Hubble constant ended decades of cosmological uncertainty. The discovery of the accelerating universe revealed that 70% of the cosmos is made of something we cannot name. The M-sigma relation rewrote the framework of galaxy formation. The pillars of creation became one of the most recognized images in the history of human visual culture. The first exoplanet atmosphere opened a field that will one day, perhaps, tell us whether chemistry like life's chemistry exists elsewhere in the universe. Lyman Spitzer died on March 31st, 1997, after completing a normal working day at Princeton, discussing astronomy with colleagues and analyzing results from the Hubble Space Telescope, the instrument he had dreamed of and fought for throughout his life. He died having seen the telescope corrected and working, having seen the deep field, having seen the first hints of the accelerating universe. He did not live to see the Nobel Prize or the full confirmation of the M-sigma relation or the ultra-deep field or the exoplanet atmosphere detections. But he had seen enough to know he was right, that the universe would reveal things from space that no ground-based telescope could ever see, that the atmosphere, the ceiling that had constrained astronomical vision for 3 centuries, was a problem that could simply, definitively be solved by going over it. There is a quality to the Hubble images that goes beyond their scientific content. People who have no particular interest in astronomy respond to them viscerally. The Pillars of Creation has been reproduced on posters, book covers, and gallery walls around the world. The ultra-deep field, with its 10,000 galaxies, packed into a patch of sky the size of a pinhead, produces a kind of cognitive vertigo in anyone who understands what they are looking at. An awareness of scale and of the profound smallness of human existence within it that bypasses intellectual analysis entirely. But alongside that humbling, smallness is something else. Every galaxy in the deep field is a structure containing hundreds of billions of stars, each one a sun. The light in that image traveled for billions of years through expanding space and arrived at a precise moment at a 2.4-meter telescope, built by human beings and released into orbit above a planet circling a middle-aged star. And those human beings, because of Lyman Spitzer's paper in 1946, because of decades of political struggle, because of the astronauts who climbed into space and fixed the mirror with their hands, received that ancient light and understood what they were seeing. That is what the Hubble Space Telescope did. It gave humanity a clear eye above the clouds and let us see the universe as it actually is: vast, ancient, full of structure and energy and light, 13.8 billion years deep, containing more galaxies than there are grains of sand on all Earth's beaches. It answered questions that had plagued science for generations. And in every answer, it found deeper questions waiting. That is what science is supposed to do. And no instrument in the history of astronomy has done it more effectively, more beautifully, or more completely than Hubble. If this journey through decades of discovery left you feeling more connected to the cosmos, more aware of what it means to exist in this particular universe at this particular moment, I hope you'll consider leaving a like and subscribing to the channel. Every subscriber helps this community of curious minds grow, and it means more deep explorations like this one can keep finding their way to people who want them. There is so much still to explore, so many mysteries still unfolding. We will keep going slowly through all of it together, one discovery at a time. Thank you for being here. Sleep well. And remember, every time you look up at a clear, dark sky, the universe looking back at you has been there for 13.8 billion years. And it is still, after all this time, full of things we have never imagined. Good night.